There is exactly one engine on this planet that achieves something engineers have failed at since the 1960s. An engine with a cycle so incredibly complex that the Soviet Union and the United States were only able to master it on paper for decades. And yet today, it stands on a test stand in Texas, firing for over 6 minutes and looking like it doesn't belong on this earth. This is the Raptor 3, and today we'll not only explain what it can do, but also why it works in a way no other engine ever has. My name is Serwan, and this is Mars Chronican. To understand why Raptor 3 is so special, we first need to understand what happens inside it, because that's where the real secret lies. Raptor uses a so-called full-flow staged combustion cycle. In German, that's called a Vollstromstufenverbrennungszyklus or Vollstromgestufte Verbrennung. You can choose. And that name doesn't just sound intimidating, it really is, because no other engine that has ever flown uses this cycle. Raptor is the only one. But let's start from the very beginning. In a conventional rocket engine, you need a way to force the fuel into the combustion chamber at enormous pressure. That's what turbopumps are used for. So, extremely fast spinning pumps that are powered by small preburner turbines. The simplest version of this is the gas generator cycle, also called the open cycle. Here, a small portion of the fuel is burned in a gas generator to drive the turbines, and then this exhaust is simply vented overboard without contributing to thrust, so energy is lost. In other words, you lose efficiency. The iconic F1 of the Saturn V, as well as SpaceX's current workhorse, the Merlin engine of the Falcon 9, use this simple but wasteful cycle. Then there's staged combustion, the staged combustion cycle. Here, the exhaust from the preburners isn't dumped overboard, but instead is routed back into the main combustion chamber and burned again. Burned again because the mixture in the preburner burns fuel-rich. So, fuel-rich, that's more efficient because less energy is wasted. The Russian RD-180 uses this cycle with an oxygen-rich preburner, the RS-25 from the Space Shuttle, or the RS-25 on the SLS uses it with fuel-rich preburners. And the BE-4 from Blue Origin uses an oxygen-rich partial flow staged combustion cycle. That means only the oxygen flows completely through the preburner and the turbine, while the methane only partially participates in the pre-burning process. If you thought that was complicated, then you better sit down now, because it's about to get even crazier. Here comes the Raptor. The full-flow staged combustion cycle takes a radical step further. Here, there are two separate preburners, one oxygen-rich and one methane-rich. The oxygen-rich preburner drives the oxygen turbopump, and the methane-rich one drives the methane turbopump. And here is the crucial point. Both exhaust streams are not vented overboard and are not only partially used. All of the propellant, 100% oxygen and 100% methane flows through the preburners, through the turbopumps, and is then brought together in the main combustion chamber and burned a second time. This time almost completely. That's even more complicated than it sounds. If your jaw just dropped, give this video some hype now. Sadly, it doesn't work for all. It's not clear to everyone who can do it and who can't. But what is clear is that it really helps the video reach more curious people like you and me. Thank you. SpaceX has taken on this mammoth task because it brings several huge advantages once you crack this technology. First, the turbines run cooler and at lower pressure because the mass flow passing through them is so much greater. Longer lifespan and higher reliability, and SpaceX says that a single Raptor should eventually withstand up to 1,000 flights. Second, since both oxygen and methane are already fully vaporized before entering the main combustion chamber, they mix faster and burn more efficiently. Gas meets gas instead of liquid meeting gas. This allows for a smaller, lighter combustion chamber while also achieving higher pressure and more thrust. And third, there is no longer a seal needed. which is required in other stage cycles to separate the oxygen-rich side from the fuel-rich side, one of the most common sources of failure in high-performance engines. The technical term for this is interpropellant seal. The reason why this cycle is so rare is obvious. It is incredibly difficult to master. In the 1990s, the RD270 was developed, a full-flow prototype that made it to the test stand but never flew. The Americans experimented with the integrated powerhead demonstrator, a project that only demonstrated the powerhead and was then discontinued. Only SpaceX managed to not only build and test a full-flow stage combustion cycle, but also to mass produce it and make it fly. Of the Raptor engine so fascinating, because what we know today as Raptor 3 is the result of a radical simplification that was only possible because SpaceX learned from 2 previous generations. Raptor 1 debuted in 2019 as a pioneer. 185 tons of thrust, 350 seconds of specific impulse at sea level, but with a total mass of over 4.7 tons, including the vehicle side hardware. Thrust-to-weight ratio of 39. The chamber pressure was around 250 bar. Impressive for a first full-flow engine, but still with over 1,000 individual parts and a correspondingly complex manufacturing process, which repeatedly led to problems. That was the Pathfinder phase. Raptor 2 came in 2022 and was a huge leap in production. Thrust increased to 230 tons, total mass reduced to 4.5 tons, chamber pressure increased to 300 bar. So we're already talking about a thrust-to-weight ratio of over 51 here. And above all, SpaceX achieved a production rate of over 1 Raptor 2 per day, at a unit price of under $1 million. Hundreds of these engines have flown since then, and of the nearly 400 that were used in 11 flights, only a handful have failed. And mind you, this is in an ongoing development program. And then came Raptor 3. And here, SpaceX did something so radical that the then CEO of United Launch Alliance, Tory Bruno, saw a photo of the engine and publicly claimed it was incomplete. Of course, he was completely wrong. The engine looks so bare because it really is that bare. Almost all external lines, sensors, shields, and covers have been moved inside and integrated into the engine structure. No more heat shield, no more fire suppression system. Only the gimbal and actuators are still visible from the outside and protected. And this was only possible thanks to a technology that Elon Musk himself says it's not widely known that SpaceX has the most advanced 3D metal printing technology in the world. Raptor 3 makes extensive use of additive manufacturing. In particular, a technique known as laser powder bed fusion and complex internal structures, which would simply be impossible with conventional methods. Cooling channels that are printed directly into the walls of the combustion chamber and the nozzle. Turbopump housings, which used to consist of dozens of bolted and welded individual parts, are now printed as a single component. Fewer weld seams mean fewer potential leak points. Fewer bolts mean less weight. And fewer parts mean faster production. And in general, a part that doesn't exist can't fail. True to the motto, the best part is no part. The result, 280 tons of thrust, 350 seconds of specific impulse, a total mass of 3.2 tons. So, a thrust-to-weight ratio of an incredible 87, that's more than double compared to Raptor 1, chamber pressure over 350 bar. And Musk says that Raptor 3 should eventually go over 3. Speaking of engineering, attention to detail, and the love for elegant solutions, I recently got something on my desk that actually reminded me of exactly this philosophy. The hover pen Interstellar from Novium. And before you wonder what a pen is doing in a space video, just listen for a moment. This pen floats on its base. No battery, no electricity, purely through permanent magnets. And steht in einem Winkel 23.5 degrees, inspired by the tilt of the Earth's axis. Mine even has the engraving Mars Chronican. And I have to say, every time someone sees my desk, it catches their eye. The hover pen is made from aerospace grade aluminum. It's refillable and you can personalize it with an engraving. For example, with a name, a date, or a personal message. It comes in 4 colors. And there's even a premium version with a real meteorite fragment that's older than the Earth itself. So, if you're looking for a gift, for example, for the upcoming Father's Day, for someone who loves design or space, or just for yourself, then this is the perfect candidate. Novium also has the hover pen future, available as a fountain pen or rollerball. With my discount code MARS1, you get a whopping 15% off all hover pens during the first 72 hours after this video is released, and after that, it's 10%. And shipping to Germany, Austria, Switzerland, and most European countries is free. Just scan this QR code on screen or use the link and the code in the video description. But let's get back to the Raptor 3 and see how it stacks up against the competition. This is where it gets interesting as we examine other Methalox engines worldwide. The BE4 from Blue Origin is the most direct competitor because it also burns methane and oxygen and is designed for reusable rockets, even though United Launch Alliance always throws them away. But the fundamental difference lies in the cycle. As mentioned earlier, the BE4 uses an oxygen-rich staged combustion cycle, which means only one pre-burner. So only one exhaust stream that drives the turbine. It's simpler, it's proven, and it works. The BE4 delivers between 240 and 290 tons of thrust depending on configuration and application, with a chamber pressure of only 134 bar, less than half of the Raptor 3. Unfortunately, there are no official mass figures, but estimates are around 5.4 tons, which gives a thrust-to-weight ratio of about 44 to 44. 50 ergebe. However, experts believe that this will improve in the coming years. The BE4 does have its advantages. It can be throttled down more than the Raptor, which is useful for precision landings. The lower chamber pressure means less mechanical stress, which could theoretically increase its lifespan. And Blue Origin has deliberately designed the engine conservatively, aiming to achieve reusability through gentle operation. Raptor 3 pursues the same goal, but with more than double the chamber pressure. That's like saying both cars want to reach 500,000 kilometers, but one drives at 130 and the other at 280. Visually, the difference is striking anyway. The BE4 looks like a classic rocket engine with a tangle of pipes, valves, and external hardware. Raptor 3 looks like someone cut away everything unnecessary and left only the essentials. When it comes to price, the gap becomes downright grotesque. A Raptor 3 costs under $1 million, with the goal of getting it down to under $250,000 US. A BE4 is estimated to cost between 8 and 20 million Blue Origin needs over a week of manufacturing time for a single BE4. SpaceX now probably produces significantly more than one Raptor 3 per day in McGregor. The serial numbers are already well into the 140s. Sen 40 was spotted in early April 2026. And those are just the engines that end up in front of the cameras. Behind closed doors, there are probably dozens more. By the way, NASA Spaceflight runs a permanent live stream there, showing the test site around the clock. Very good job. During that period, they counted 40 Raptor tests alone. The longest of those lasted 348 seconds on the vertical test stand. 19 different Raptor 3 serial numbers were identified during this period. And even the rare vacuum variants are appearing more and more often, like RVEC SN77, which was spotted at the end of March 2025. But the Methalox revolution is not limited to America. In China, Landspace launched the world's first methane-powered rocket into orbit with the Suqianqiang in July 2023, powered by 4 TQ-12 engines. The TQ-12 uses a gas generator cycle, delivers around 67 tons of thrust at sea level, and is therefore in a different league than the Raptor. But that's not the point. The point is, Landspace launched the Suki 3 in December 2025. The Suki 3, made of stainless steel and voted on by Report in 2012, is powered by 9 TQ-12A engines that together generate around 700 tons of thrust. The second stage reached orbit. The first stage exploded shortly before landing. But the mission was successful and the attempt itself was impressive. Landspace plans to reuse each first stage 20 times and wants to offer commercial launches for mega constellations starting in 2026. What we're seeing here is a global Methalox race. SpaceX leads with the only full-flow engine in the world. Blue Origin flies the BE-4 on New Glenn. Landspace flies in China. And in addition, there are other Chinese companies and government programs working on Methalox engines. Methane is the fuel of the future. Cleaner than kerosene, more practical for reusable systems, and can be produced on Mars. But only Raptor uses the cycle that fully exploits the potential of this fuel. And this very engine is now about to make its first flight. Booster 19, the first Block 3. Super Heavy was lifted onto Pad 2 at Starbase in early March 2026, initially with only 10 Raptor 3 engines. On March 16th, a 10-engine static fire was conducted, marking the first time that Raptor 3 was fired on flight hardware. All 10 engines started successfully. Although the test was terminated early, the reason was on the ground side, not with the engines. SpaceX then brought the booster back to the production facility to install the remaining 23 engines. A 33-engine static fire on Pad 2 is imminent. And then comes Flight 12, the first flight of a complete Block 3 Starship stack. And the very first launch ever from Pad 2? What fascinates me most about Raptor 3 isn't a single number. It's the convergence. It's an engine that uses the most complex combustion cycle ever flown, yet still looks simpler than anything that came before it. It delivers more thrust while being lighter at the same time. It achieves the highest chamber pressure of any engine ever produced and cools so efficiently that frost forms on the nozzle during a 6-minute test. And it can be produced for less than $1 million in less than a day. None of this can be appreciated enough. There is a pattern in the history of rocket technology. Simplicity is the result of deep understanding. The F1 engine on the Saturn V was brutal in its power, but simple in design. The Merlin engine on the Falcon 9 is the workhorse of commercial spaceflight, precisely because it's so uncomplicated. And Raptor 3 continues this tradition, only at a level that was considered impossible 10 years ago. Because the full-flow stage combustion cycle was considered an academic exercise for decades, something you read about in textbooks, but in practice, it doesn't work. SpaceX has proven that it works. And now they're producing it on an assembly line. Literally, if you enjoyed this deep dive video into the technology behind the most impressive engine of our time, then subscribe to Mars Chronican and leave a thumbs up. A huge thank you goes out to all channel members and Patreon supporters. If you also want early access to our videos, you can find all the information about it below in the video description. And if you're still looking for the perfect gift, don't forget, with the code MARS1, you get 15% off all hover pens from Novium, but only for 72 hours. The links are in the description. My name is Serwan, and this was Mars Chronican. Thank you for tuning in. Per aspera ad astra. Best part is no part. I'm still filming. Give me another 20 minutes, please. Could you please move the train somewhere else? Could you please move the train somewhere else?